All right, good afternoon, everybody. Welcome to the last seminar of the academic year. And before I hand it back over to our grad student organizers, Daniel and Savannah, I'd like you to ask me to join me in giving them thanks for organizing this for the last semester. Thank you very much. I think it's a really important service, and I hope that you also get something out of it in terms of being able to interact with researchers in your field. We're now back mostly live, so you get to go for lunch with them and all that. And anyway, so thank you very much. It's highly appreciated that you do this. It's a very, very good, very great service. And we made little plaques for you that will remind you of this wonderful time. Okay. And it's actually made made out of premium alder, so it also provides a little bit of heat when you need it. So down the road, you know. So good. Eventually. So good. Thank you again. Pleasure. Go ahead.
Okay. Hello, everyone. Please, students, remember to sign your name. And today we have a special guest, a really special one. So it's Liz. Liz, she's coming, she's visiting us, not coming back home. She's visiting us today, but she's from here, from UNH, from CCOM. So Liz is a postdoctoral fellow with the Marine Physical Lab at Scripps Institution of Oceanography, where she's using broadband split beam echo sounders to characterize the ice-ocean interface, gas bubbles, and thermohaline structure in high-latitude glacial fjords. She received her PhD in oceanography jointly from the University of New Hampshire and Stockholm University in 2022. Next January, she will join the faculty of the University of Connecticut. Thank you. As an assistant professor of coastal oceanography with the Marine Science Department to continue her research efforts in polar systems. So please welcome Liz.
Well, thank you, Daniel. Sorry about the thermohaline in Connecticut. Those are tricky. Yeah, thanks for having me back to give a talk about my postdoc work. So I'm going to be taking you all far to the north to Svalbard to think about an important and climatically sensitive part of the polar seas, which are marine-terminating glaciers or Tidewater glaciers. And these are, maybe you can see in the background of the slide here, these are locations where the terminal end of terrestrial ice fields, so ice sheets, ice caps, glaciers, interact directly with the ocean at this interface, the terminus of the glacier. And this is the location that I am studying using high frequency broadband acoustics. So just to start out, I want to put my acknowledgements all up front. So first off, work is funded by the Office of Naval Research, Ocean Acoustics Division. My time is supported by the Scripps Postdoctoral Fellowship. Lots of collaborators here. Two that I'll just point out are my postdoc mentors, Grant Dean and Fiamma Stranio, members of the IMT and the MOD group at Scripps. And then I have some collaborators in both Singapore and Poland who were present for the field work as well. And then just special thanks, Tony is here, Larry is not, but thank you to both of them. They lent me the equipment to do this research because my equipment was tied up with supply chain issues. Yeah, and money, no, I had the money. But. And then the captain and crew of MV Ulla Riemann supported the work, as well as the crew of the Polish Polar Station. That was where we were working out of when we were in Hornsden. So I want to start with sort of big picture, the broad research goals that are defining my time at Scripps, my postdoc, but also, as Daniel mentioned, sort of the first few years, maybe all of the years that I'm at Connecticut. So the first is to collect acoustically derived observations at the ice-ocean interface, which, reasonably you might say, well, that seems pretty basic, Liz. If you can't even collect the observations, how can you do any other work? And that is true, right? I mean, the observations are key, and this is a really challenging region to work in, and so I'll talk a lot about that. And so this is really sort of a test at the beginning of the postdoc to see whether or not these measurements could be made at all, and if they could be made, were they quality measurements that we could use to basically evaluate research goals 2 and 3. So assuming the data looked good, and it did, we could look into providing measurements of the submerged terminus, both its position, right, so where it is in the water column, but also its geometry. And I'm quite interested in these measurements specifically related to processes that alter glacial stability, right? The other dynamic that I was interested in studying was subglacial discharge plumes. And I'll talk more about what these are and where they come from. But again, this is a connection to glacial stability and a process that's very, very poorly constrained in the literature because it's so difficult to make measurements. So before we get into sort of the how of these measurements being made, what kind of measurements were they, let's talk a little bit about the why. So if you are a polar oceanographer, there's lots of reasons why, right? Marine terminating glaciers support really interesting biological communities in high latitude fjords. They alter thermohaline structure, they impact circulation, they do all sorts of things, right? But I'm not sure if anyone here, there might be a few people who are polar oceanographers or work at the poles. If you're not, one of the reasons we might care about marine terminating glaciers is sea level rise. They're an important component of sea level rise. You're probably aware sea levels are rising, hopefully, yes, maybe. Yeah, okay, so these are the IPCC curves from the most recent report. These different curves represent different carbon emission scenarios, right? Projected out into the next century, so by 2150, maybe some of you will still be alive, I don't really know. Half a meter to over, coming up on 2 meters of sea level rise are predicted, right? So this is a major issue. It's gonna affect many, many people, something like 80 million at minimum, primarily in low-lying nations, island nations, but this is not an issue that is developing nation over there. These are pictures of Hampton Beach here in New Hampshire, right? Flooding more and more commonly. So this is impacting, everyone in this room to a certain extent, right? And so then the question, of course, being, where do glaciers come in? Well, glaciers come in, if we think about the drivers of the global sea level budget, right? What is causing sea level rise? Historically, 80s and 90s, mostly thermal expansion of the upper ocean, starting in, say, the 2000s up until now. You see these gray, varying colors of gray lines. And these are standalone glaciers, both in northern and southern latitudes. So Alaska as an example, Greenland and Antarctica, right? This is fresh water that's tied up in the terrestrial system in the form of ice. As it melts, it's adding to this budget. How do marine terminating glaciers fit into it? Why do we care about studying them in this context? Well, that's because they're the conduit, right? So here's Greenland. Color here is basically speed of ice in kilometers per year. So red is very fast, blue is very, very slow. We can see that there are these fast speeds on the edges of Greenland, and if we zoom in to a couple of glaciers that I'm not going to try to pronounce, don't even know how to do that, you can see these really deep red colors. This is where the ice is flowing, these are ice streams, and this is where the ice comes out, right? So the mass loss and the introduction of that fresh water is happening at these systems. Now, the way in which that happens is typically referred to as ablation, and there are 3 primary ablation mechanisms that we think about. One you probably are aware of, right? Calving, aerial and submerged calving events, big pieces of ice falling into the ocean, popping up into the ocean. Next, you have glacial discharge, and this can be from the surface, right? So this is basically when the ice melts on land, and then that fresh water is transported to the ocean. So surface melt, but also subglacial discharge. And you probably guess, subglacial discharge creates subglacial discharge plumes. And these plumes, right, fresh water comes up, it entrains a lot of relatively warm water, right? Not warm to us, but warm to the ice for sure. And that moves up the face of the glacier, and it enhances the final form of ablation, which is submarine melting, right? So this is the melting of ice in the ocean, right? So these glaciers are partially submerged. As the ocean warms, right, it warms the ice, it melts. Plumes in particular, there's a feedback loop between these 2 things. So these forms of ablation, right, they add to these curves, right? That's part of the models, right, that are driving these IPCC curves that can tell us what's going to happen to sea level. And what I want to point out here, what is really driving my work, is the uncertainty associated with these, right? So even in this sort of likely range, medium confidence, we're still talking about sort of plus minus 1.5 meters. And that's going to matter for a lot of people, whether or not it's, sort of minus that 1.5 meters or plus that 1.5 meters. What drives that in part, it's not the only thing we don't know, is poorly constrained contribution from ablation. We have a sense of calving, we can watch it happen, right, via satellite imagery. I'm not sure there are any measurements of submarine melting in the literature. I don't think it's been directly measured by anyone on a broad scale, right? So we do not understand, how that's going to contribute to these curves. Not included in these models at all are the feedbacks between the ice and the ocean. As the ocean warms, it's going to increase, right, submarine melting. It's probably going to increase calving events. And we don't know how subglacial discharge is going to change. Not parameterized, not in these models, right? So that's what drives my work, is trying to better understand these systems. So as an example, we can better predict sea level. Although there's lots of other reasons we might be interested from a polar perspective, right, about these systems. So the reason that we don't have measurements is because this is what these systems typically look like, right? So we're in a high latitude fjord here in Alaska, right? Head of the fjord is the ice face. The mouth is, somewhere down over here. Geographically isolated, it's hard to get to, right? It's far from population centers. Once you're there, you have to get to the terminus. There's often a large amount of ice in the way. If you're not in the right kind of ship, you can't even get there. And once you get there, when you want to make your measurements, you're in serious danger. People probably have a sense of what this is, right? Calving events, right? These are big, big pieces of ice, right? And if you try to make measurements down here and this falls on you, you're gonna die, right? And even if you send equipment here, the equipment is gonna, effectively die, right? The equipment is gonna be crushed, it's gonna be damaged. So it's really hard. It's really hard to make measurements here, direct measurements. Now, I don't wanna say that people don't make measurements, because they do, and they do it in really creative and unique ways. And I just wanted to highlight some of the crazy things that people do. Amazing crazy, not like a bad crazy, right? Helicopter deployed, XBTs, they're flying above the ice face and dropping equipment in, right? Not a lot of measurements, but they can make measurements. Obviously, unmanned vehicles are big, and they're becoming more and more common as the cost of those vehicles is dropping, right? And as the vehicles can do more. Again, the vehicles are still potentially going to get crushed, and while you wouldn't die, I know a lot of people who emotionally would die if their vehicle got crushed. The coolest one is using animals, so putting effectively CTD sensors on ringed seals, releasing the seals into the ocean, and then they forage at the ice-ocean interface, and they can actually collect the measurements. And assuming you can catch the seal again, then you have some direct measurements there. But you can see how we have struggled to constrain these systems. And so I'm sure you're aware, especially those of you who know me, what I'm going to suggest we do. I'm going to suggest that we use active acoustic tools to make measurements in this region, right? So active acoustic tools provide us with remote high-resolution observations of ocean boundaries and water column process. So I have a couple of examples here, right? Looking downward, typically, we can look deep into the ocean. So thermohaline staircases in the central Arctic, right here, 100 to 240 meters away from the transducer face. A lot shallower here, this is in the Connecticut River, looking at shear instabilities. But we can use this to our advantage, right, to make measurements remotely of this space. And then they also provide us with this important spatial context, right? Especially in shallow environments, you can fire really, really fast, right? Which means that you can collect information about the evolution of processes that are occurring in the water column or of bathymetry or other boundaries. So here, looking at thermohaline staircases evolving over, I don't know if you can read that, that says 91 kilometers, so really, really long distances. In the Connecticut River, this is much shorter distances, but we can see really, really high resolution imagery of these shear instabilities. So we can take this and we can leverage that to study these systems. I use high frequency broadband split beam echo sounders. Sorry, Daniel, I know that's a mouthful. And these systems provide us with a couple of other tools that we can utilize. So the first thing is that because we're using high frequency broadband pulse, we can use pulse compression signal processing to achieve resolution, in this case, vertical resolution, so of individual profiles in the order of centimeters to millimeters. So that evolution of processes that we can see is really highly resolved, more so than other systems. Here, we can see individual bubbles rise through the water column. We can use split beam processing to track those bubbles across the beam, and we can get out their vertical trajectory. We also have frequency-dependent scattering information because it's a broadband pulse, so we're sweeping over a range of frequencies. So we can look at scattering as a function of frequency. And we can take these observations and we can combine them with theoretical acoustic scattering models, right? So these are first principle physics, predicting how something should scatter sound based on physical parameters. We can combine that model with our observations to, for example, measure bubble radius from our acoustic data, right? And so that's called acoustic inversion. And so we can take each of these tools, and my plan is to apply them to these high latitude systems. So returning back to the research goals, the first goal, right, is to just do the data collection. See if we can, right? See if we can get to this interface, see if we can use these systems, see if they're useful in observing those processes that occur in the water column, subglacial discharge plumes, see if we can get at geometry and position of the terminus. So, field campaign, right? I mentioned this has happened in Svalbard. So this is this island far to the north, working in southwest Svalbard in a place called Hornson Fjord. Highly glaciated fjord, 8 different glaciers, 7 of them marine terminating. We have 1 land terminating glacier over here. Working in Hansbreen, so this is a glacier that's been studied since the mid-60s, so it's pretty well defined regionally, mostly by Polish and German scientists. And I was working with a group, the International Partnership for Acoustic Observation and Monitoring of Glaciers, which has the acronym IPAOMG, because Grant wanted it to be easy to remember, so I think it is. And this is a group that studies ablation using historically, not anymore, of course, using passive acoustic tools, right? So some of the other things that were being looked at during this field campaign, including detecting calving events and quantifying them using passive acoustics, studying the melt signal of the actual terminus. So when glacial ice melts, gas explodes out of it. It has a lot of entrained gas, and so it sounds a little bit like bacon frying, basically. And then the last thing is looking at sub-millimeter scale ice-ocean interactions as well. And then, of course, I added in some active acoustics to this work. So the ship I worked on, I mentioned, MV Ulla Riemann. This is not an icebreaker, but an ice-enforced vessel. It used to be basically a first aid vessel. I mentioned I borrowed some equipment. So this is Tony's ES200 7CD split beam transducer. It's connected, although I don't have the picture here, to Larry's EK80 WBT. So 100 kilohertz of bandwidth, range resolution on the order of about less than a centimeter, basically around a centimeter. And I deployed that right here via this side-mounted pole. It's pulled up right now, but when we transmit, of course, it goes in the water. 2 different types of ground truth data. I won't show any of that because it's not for the project I'm talking about here, but I'll just note that they are deployed. We have a Epsi-Fish microstructure probe and then a Vailport mini CTD. So I mentioned 2 geometries. First one is sort of the typical geometry we might expect, right? A downward-looking geometry. These are how the systems are often deployed. This was for a project looking at thermohaline structure and mixing in the fjord associated with the tides, associated with the sills, but we're not going to talk about that. We're going to talk about the more exciting data set, I think, personally, which is this side-looking geometry. So not quite horizontal deployment, right, down with a 10-degree declination angle using this kind of little modifier plate. And that was just so we didn't lose a lot of energy upwards into the fresh water that tends to be near the surface. And so when you see the echogram, which I'll show you in a few slides, what you're really looking at is this sort of diagonal slice through the water column, starting at about 2.5 meters depth, and then coming down to intersect with the ice face between 20 to 25 meters depth. Just keeping that in mind. So the actual scans. So this scans of Hansbreen happened in one day, July 9th, over about a 5-hour period. So here we have some nice satellite imagery. It's not up to date because the actual position of the interface is this dotted line as of that day in July. And this black line is just an example of what one of those scan lines looked like. So because of our geometry, we ran the lines from the east to the west because the pole is on the starboard side. So you can kind of imagine, right, we sort of drive trying to stay as parallel as possible to the exposed ice face, although we don't know what's happening underneath. In general, the passes were about 1.2 kilometers. It took about 35 minutes to collect one of the passes that I will show you. And we did collect GoPro time-lapse imagery. So I'm gonna hopefully play this and it's gonna show you what it looked like condensed. Oh yeah, look at that, it's working. So that's 35 minutes condensed into 10 seconds. We can watch it again. Woo! There we go. So you can see this like little, it's a boat hook, and we use that to push icebergs away from the transducer, basically. And so we would run east to west, and then we would stop, we would come back, and we actually would take CTD casts again. But today we're just going to focus on the acoustic data. So this is the echogram, right? And I think you, other than a very short presentation of ocean sciences, you guys are the first ones to see it. I haven't really published with any of this work yet. So here, as a reminder, right, we're looking from about 2.5 meters depth out, right? And this is range away from the transducer phase, down into the water column, and then we have the ice-ocean interface at about 20 to 25 meters depth. In terms of resolution, I mentioned vertically here, so a long range, resolution is about 1 centimeter, and then in between individual profiles, so they're all stacked up here, we have on average about 50 centimeters between profiles. So we could fire quite quickly. So I'm just gonna give you some sort of qualitative observations, and then we'll get into quantitative analysis. So first, there we go. This is the submerged scattering from some icebergs. So we call them birdie bits. They were in between the ship and the ice face. And to just give you an example here, that's them. And they're about 5 meters across at the surface. So that's kind of the scale here, just to give you a sense. Now, the strongest scatterer by far is the actual ice face, so the ice-ocean interface, the terminus. I'm going to talk about this in detail in a few slides. The most exciting part of this echogram is right there. So that is a subglacial discharge plume. As far as I'm aware, there are no measurements of this width ever made before by anyone. So this is the first ever measurement, basically seeing the plume coming out and seeing the surface expression. I'll talk more about this again in a few slides. And then over here, there's a lot going on actually. Potentially an additional plume, a weaker one, a lot of potentially biological scattering also. We don't really see any other biological scattering in this echogram. So not entirely certain what this is, but just a note, right, still a mystery to be solved. So as far as sort of testing out whether or not this can be done, I think we can say that it can be done. There are things that I learned from this deployment that I would change in the future, but just wanting to note, right, I think we can leverage these systems to make these kinds of measurements. And so now that we've made the measurements, what can we do with them? And so the first thing we're going to talk about is the submerged terminus. So again, we're going to start with some observations, and then we'll get into quantitative analysis. So first off, scattering from the terminus, -35 to -55, calibrated and corrected surface scattering strength. The thing that's most obvious just by quick observation is the variability here in range from the acoustic transducer to the terminus, right? This is over 80 meters of variability that's occurring. Now, some of that is because the ship did not stay perfectly parallel, right? We had to avoid icebergs, we pulled away, especially in this region, but we did not pull away 80 meters, right? This variability suggests that potentially there are variable, if the terminus, we expected the terminus to be flat, there are variable rates of submarine melt, or there's variable rates of submerged calving that are occurring. Those are the kind of things we want to understand. There are some other things that suggest that the geometry here is really complex. The first is the presence that you can see here of these sort of shadowy returns. Those are side lobe returns, so they're not from the main beam. They occasionally appear, and in other locations we don't see them at all, again suggesting complex geometry. We see variability in the actual return from the interface itself, right? It's an extended surface return, and we'll talk about what that means, but the actual length here, vertically in each ping, varies by almost an order of magnitude. So here, about, if we were to project it into space, about 10 meters, but over here by the subglacial discharge plume, it's less than 1 meter in length. So there's a lot of variability in the length of that return. And then finally, we have this region of crazy double returns, not from the side lobes, but from the main beam, that we're seeing basically a return on the ice, and then later in the return we see the ice again. So really complex geometry. The way that we quantify this is actually by taking advantage of the split beam system. So we're going to use split aperture analysis. And so here, have many of you seen this image before? Anyone who's taken John's classes has seen it. So I don't think John is here today, but this is a John Hughes Clark image. This is showing the effect of increased oblique incidence on footprint projection on the seafloor, right? So as the oblique angle increases, we get this elongation of the footprint. The footprint becomes pulse length limited, and the pulse actually propagates across that footprint. Now, this is for a steered multibeam, right? But the geometry is actually pretty similar to what I'm talking about. I'm not steering the beam. The actual system is static, but the interface is tilting, right? And so it creates the same situation here. When we steer, so when this angle theta increases, we increase that echo envelope length because the pulse propagates, and we also can see, if we can compute it, this phase ramp, which becomes less and less, the slope becomes weaker and weaker and weaker. Now, the phase ramp we can actually use to estimate theta directly, and we can get at this phase ramp from what we call split aperture target analysis. We look at the return from our array to subapertures of our array, and we compute the phase offset. So this phase offset is a function just of this basically path length difference. So as the pulse propagates across the footprint, we get this variable phase related to this path length difference. And so we can extract theta from that. In principle, what that looks like, again, this is our terminus scattering, but instead of coloring it by intensity, I've now colored it by the angle associated with the transducer in the fore-aft direction. So that's the vertical plane, right? Blue is at the top, yellow is at the bottom. If we look at two examples, if we're at normal incidence, so this, the general slope of our ice face is perpendicular to our incoming acoustic wave, we will not see a phase ramp, right? And we will see a relatively short acoustic window echo envelope length. If we take that ice face and we make it really extremely obliquely incident, that pulse, the footprint will increase, the pulse will propagate across the footprint, and we expect it to propagate from the top, blue, to the bottom in yellow. There's an example right here of that happening, blue to yellow. We see this strong undercutting. We see the opposite happening over here in this corner, where we actually have a positive slope phase ramp. So we have, in fact, overcutting. So instead of the ice being tilted down, it's tilted back like this. And then in this odd area right here where we have this double return, we see both under and overcutting at the same time. Now, there's a huge amount that can be done with this information. We can use the zero phase crossing to position the ice face in the water column. We can see where it is very specifically. We can also get the tilt angle at that position. So what's the geometry of the ice face? So that's still analysis to be done, but I can tell you from some preliminary estimates, these three and a few others, what the general undercutting or overcutting of the ice face is. So we have measurements from the ship's radar of the exposed position of the ice face, and then we have these zero phase crossing measurements, and those suggest that the whole ice face is undercut by between 1 and 4 meters, right? So that's pushed back, that at each of these positions that we see, we have variable geometry. This is all with the goal of looking at the angular dependence of broadband backscattering. So we have our split beam echo sounder that we can take advantage of. We have this natural variability in the glacial geometry, and this provides us with variable incidence angles. Now, what those angles are is dependent on the glacier itself. We don't have any ability to move the system, right? The acoustic angle is set. And so that provides us with the potential of looking at the angular dependence of backscattering, right? So looking at basically what our incidence angle is and how that modifies the scattering intensity. This has been done for many different types of seafloor sediments, right, with the goal of inverting for seafloor sediment properties. And we can combine this analysis with our broadband spectral analysis. So look at scattering at each of these angles, not just as a function of angle, but as a function of frequency as well, because we have broadband data. I didn't show you any of that because I haven't done that analysis yet, but this is work that has been done in the past, looking at broadband backscattering from different types of seafloors, and this was done by Tom Weber and Larry Ward here. And so this is something that could be done, again, at the ice-ocean interface. The long-term goal of this kind of analysis would be to work towards geoacoustical inversion for ice parameters, right? To be able to look at acoustic data and extract the age of ice, the amount of gas held in the ice, right? The ice's roughness remotely using the acoustic data. That's the work of probably multiple scientific lifetimes, if I'm honest, but we can work towards it. So now, I only have a few minutes left, so I want to just discuss briefly the dynamics of the subglacial discharge plume. So first thing would be to just show you what it looks like. We knew there was a plume here before we ever collected the acoustic data. We came out this day And we saw just from afar, really intense surface roughness on the actual surface of the ocean near the glacier. We also saw this evolving sort of ring of ice melange moving around, surrounded by this pool where we saw the surface roughness. And I'm gonna play this video. If you get a little bit seasick, maybe don't watch because it bounces around a lot. But this is what the surface looked like near the ice face, where we knew there was a glacial plume, right? So you see this roughness, you see this movement, you see billowing up happening right here, right? As if you're like in the bath and you kick upwards, right? And you create sort of a little plume of your own, right? So we knew there was a subglacial discharge plume occurring here, even before we collected the acoustic data. I did not take this video, somebody else did, I borrowed it from them. My video would not have moved, but you can really see the variability here. So this is the echogram. We've seen it before. So first off, right, the plume, much weaker scatterer than the ice face. It's not exactly an apples to apples comparison because this is volume scattering, but -55 to -85 dB. The strongest scattering by far occurs right where the plume comes off of the ice face, right? So in these two sort of discharge locations, you'll note that we actually have two plumes. So if we zoom in here, right, these are actually individual. They appear to be individual plumes. So at this location where the scattering is the most intense, these are between 4 and 6 meters in width. So they're not small, right? It's like the height of this room, maybe, something like that. Someone nod, I'm not entirely sure. Yeah, Jamie.
I'm just a little confused about the geometry. So this is like a narrow sheet that's...
I'm gonna talk about the
Okay.
geometry, don't worry, yeah. So these plumes, where they are, 4 to 6 meters in width, and then if we come all the way out to where, we're the shallowest, we're looking at the surface expression, this is over 350 meters wide, sort of along the ice face. Now, good question, because it's very unusual geometry. What exactly are we looking at here? So this is the vertical cross section of what we might expect to see from a plume, right? The plume's released at the bottom of the ice face. We're sort of, we're swimming in the water here and looking at it. It rises in this core, which expands, right? Because it's entraining, water from surrounding it. And then the surface of the ocean is here. It hits the surface of the ocean and then it moves outwards, right? Because it doesn't continue up into the air. So we get this kind of shape if we're looking down, sort of at the ice face. So initially, we're in this region, right? We are insonifying basically this pool component where we see this surface expression, we see intense scattering, we see a lot of eddies, right? We see a lot of eddy structure, we see strong scattering, but we don't actually see the plume at the ice face. So here we're running along the pool, and then as we drive, we start to come up to the core, and here we're actually insonifying across. We're seeing the entire plume, including the core and the surface expression, so we're on sort of line number 2. And then once we pass this core, we're back into this kind of plume, this kind of pool feature as well. Now, you'll note that on the left versus the right, they're not symmetric, right? That isn't because we slowed down or anything like that. We actually see much weaker scattering on the west side versus the east side, and it's shallower as well. These eddies drop down to more than 5 meters in depth. We see some deeper eddies here. Here, we're really seeing eddies only to about 3 meters in depth below the transducer face. So that suggests to me, in some ways, that there might be some kind of potential westward surface current happening. Plumes are suggested in much of the literature to influence circulation in fjords, but this is an item to dive into in the future. The other thing that we need to dive into is to try to determine what's driving the backscatter signal, right? So the plumes are highly turbid, so there's a lot going on here. There's a lot of mixing, so there's potentially turbulent microstructure, right? So it could be entirely a mixing signal. We do see the strongest signal in sort of the core region, but plumes also carry suspended sediment. They also carry gas bubbles. And so it could be that what we're seeing here in terms of scattering is actually the advection of passive tracers. And all of those things scatter sound as a function of frequency in very distinct ways. So we should be able to pull apart what is causing the scattering that we're seeing here. In terms of the applications of this data, of course, I kind of already mentioned it, but we know in the literature, there's been plenty of work that has suggested that these plumes enhance submarine melting. They also carry all sorts of different things. They carry fresh water. They are part of the heat budget. They bring in sediment. But all of the work to sort of connect them to submarine melting is really just connected to modeling, right? And these models are not well constrained. Like I mentioned, there are no measurements of this core width. No one's ever been able to measure that. We've been able to try to infer it using the models to infer other models. We don't know this width of the plume coming off of the ice face. We don't know the width of the depth of the pool. So if nothing else, those broadband measurements can inform those physical metrics. But we might also be able to answer some questions about the velocities and the exit conditions as well. And so I want to just wrap up in the last few minutes, looking to the future. In terms of sort of the broadest goal, yes, we were able to collect these measurements. There are some lessons learned that came from this first deployment. Some of that is just the need to collect more measurements, right? There just are very few measurements out there to go to other glaciers other than Hans, to work with variable geometry to study the base of the glacier rather than high up in the water column, to work with additional frequency bands, right? There's a lot of potential here. I'm happy if people are interested to hear about it, to talk about other lessons learned, but I don't want to get into a sort of session where I complain about my decisions. Second, if we're talking about the submerged terminus position and geometry, there certainly is the need to extract these measurements of the Hans Green ice face tilt. So we have not just the fore aft that I mentioned, but also the port starboard, right, which is sort of the tilt in this direction, if that makes sense. I'm also interested, as I mentioned, in exploring this frequency-dependent backscattering, especially with respect to the location of the subglacial discharge plume. How is that plume potentially impacting the geometry of the ice face, right? We have the connection of both those measurements. And then finally, I've mentioned the plume already and what I'd like to do, geometric measurements to evaluate the current models, and then determine the mechanism or mechanisms deriving the backscattering signal. And I saw plumes at other glaciers as well. I just showed you one example here. So to compare and contrast the signals there. All of that, of course, looking to better constrain these systems so that the models that are run here can include those ice-ocean interactions and also can be better constrained in terms of ablation rates. And I think that might be everything that I have. Yeah, thank you.
Okay, now we're open for questions.
Yeah, very nice talk, thanks. I'm wondering if there's any opportunity to use Doppler to measure the velocity of these things.
Yeah, I think that, so, from an ADCP, I think it might be possible. I think one of the biggest challenges, I'm not super familiar with ADCP data, but if you were to, the primary velocities here are the vertical ones, and those are the ones that really matter for the models. And so to get at the vertical velocity, I think it would be best to deploy the ADCP looking down. Is that true?
You could probably have a bit of a tilt.
Okay, yeah, because just of the way that the bins are summed, I wonder if you would be able to get at. So the question, of course, being how comfortable are you getting your ADCP close to the ice face, right? If you're comfortable putting it onto a, some kind of small vehicle to deploy, I think it's definitely possible, and I think it would be very useful to have those measurements. But I think if you needed to deploy it sort of downward or sort of to the side, there's just the reminder that, right, in that echogram, that's like 100 meters away from the ship, right? I mean, you have to get it right up close to the ice face to get into the core of the plume. That's where that plume core is. So I think, those measurements would be very useful, but you'd have to be willing to sort of put the piece of equipment in danger for sure. Unless you could deploy it to the side. But I imagine if you did like a side facing or tilted like this, I just don't know if it
you
would.
could hit it at an angle and then
Yeah.
get a component of the velocity.
Yeah, and I think if there was a potential to do like a component of the velocity, that could be useful. I'm just not super familiar with how they can be deployed. Yeah.
Carlos drive his kayak.
What now?
Didn't Carlos Moffat drive his kayak with an ADCP?
So there are kayak and there's like the jet yak. Is that what you're talking about? I haven't seen any ADCP measurements. I think there might be one. They didn't get all the way to the core, from my understanding of that paper.
And
But
it
there
did get
are.
smushed.
And did it get smushed?
But they got it all back.
But they got it
tied-
back, so,
They
you
tied
know.
floats to everything.
Yeah, everything has floats on it. Everything is, positively buoyant so that hopefully you can at least get the data back is kind of, plan B and plan inside of plan C and inside of plan E kind of situation.
It was a direct carbon measurement.
Raise your hand.
I was curious, like, what do you think about adding a multi-beam to your kit?
Yeah. What I would say about multibeams is that they require significantly more complicated setup. I think multibeams, if there are any angular misalignments, the data can be very challenging to work with. And vessels of opportunity, it's hard to put a multi-beam on a vessel of opportunity from personal experience. So I would say if there was a multi-beam that you felt confident, I felt confident, someone felt confident in deploying, for the point being quality measurements are key here. I think a multi-beam would be absolutely the tool to use, especially to look at the geometry of the ice face. Much higher resolution, much more straightforward processing than the EK system. But the EK system doesn't require much beyond just a little motion sensor, and you really only care in this case about roll. And you can do a pretty rough, sort of lever arm offset situation, which is all we had, right? We only had the ship for 10 days. It took us 2 days to get the EK system set up, and that was to make sure, electrically there wasn't any interference, all of that. So I think a multi-beam, I didn't go for a multi-beam because I knew I couldn't do it in the time that I had. But I think if you were confident that you could, or you had a really ace team, or you had extra time, then it would absolutely be the tool that I would choose to do the geometry measurements. At least from a geometry perspective, you can't invert multi-beam data the same way you can invert EK data. So there's that as well.
You decided everything on one pool.
Yeah, I think that kind of field kit is sort of the idea for the future, but for this particular process, it was just limited funds and limited time and limited personnel to make everything happen, so.
Yeah, it's probably a matter of how we define terms, but in the engineering world, we would call the sketch that you sketched a natural convection boundary layer next to a vertical wall, right?
Yes.
But it's not really a flat wall. And it's losing mass, so it gets complicated very quickly.
Yes.
Overall, do you have any sense if you would try to come up with a non-dimensional parameter for this, Rayleigh number or something of how large they get in this kind of flow? The density is a function of, I guess, temperature and salinity, right? So
I think yes, temperature and salinity, and there's been a fair amount of research that's been based on modeling that has modeled them as effectively these buoyant plumes that are constrained by a wall. And a big part of what the limitations to those models is both what's the exit parameter, what are the flow rates, which are guesses, right? What's the size of the exit? But also what is the effect of the fact that the wall is neither flat nor necessarily vertical. And most of the assumptions are, let's just take it as a flat, face, and we'll just tilt it a little bit. And so people have done a little bit of work looking at undercutting versus overcutting and plume evolution. I don't know the non-dimensional parameters off the top of my head, but they're definitely out there.
But you get well into the turbulent regime, right?
Yeah, yes, definitely.
Anyone else?
Yep.
We have one? No.
What's the sort of, I guess, maximum depth that you could see this kind of working to, right? Your measurements are of the terminus,
Yeah.
relatively close to the surface.
Yeah, so I think, so the maximum sort of range, right, which would be sort of the metric, is strongly frequency dependent. So at 200, sort of center frequency 200 kilohertz, I would say, no more than maybe in a really low noise situation, maybe, 200, 250 meters. The challenge being though, certainly you can get the scattering back at 250 meters, but you have to remember that the beam volume is growing pretty rapidly, right? It's a 7-degree circular beam, so 3.5 degrees, and half beam. So then the area insonified becomes very large, right? And so then you might be insonifying the plume, but you might also be capturing a lot of ice at the same time, right? The face, the geometry means that you're probably going to encounter the ice on the leading edge of the plume before you leading edge of the beam before you see the plume. So the closer you could be, or the more narrow of a beam you could use, the better, which is the reason that the multi-beam would be key if you really wanted to get at geometry, especially if you're working in deep water, right? And the glacier face, and the glacier is grounded at 1,000 meters or something. In Greenland, these systems might not be ideal. You would really want to be working near to the surface or putting them on some underwater vehicle that could get close, which brings up all sorts of other issues, of course. So challenging region to work in overall. Yeah.
I'm new to this, so I'm wondering, how is the motion of the boat taken account for in that changing geometry and the changing?
So we have a inertial motion sensor, which collects data, and it has lever arms put in, and so we can do a correction so that we can at least know the motion associated with the transducer. The main motion here, because it's side mounted, is the roll motion. Heave is normally what you care about, but here, because it shifts it up and down. So you can account for the effect of the motion, but you can't change where the sonar actually collects the measurement, right? So if you imagine, sort of a flat face, right, and we have sort of motion, I can account for the fact that my motion is like this, but I can't change the fact that I collected a path like this, if that makes sense. So my measurements of, say, terminus, position and geometry will be along this path, if that makes sense. So if you wanted to know exactly what's happening in like a perfectly, straight line at a particular depth, you're not going to be able to do that, or you'll have to interpolate between, points that are at that depth. But you can account for motion for sure, yes.
So I just can't stop thinking about the seals that you mentioned.
Sure, okay.
I'm sorry if this is just like a joke that I just fell for it, but because I feel like there's a chance that that's
it's
happening.
real, it's absolutely real, yeah.
I was just wondering what the logistics are / advantages if there are any of like getting like useful data from these seals. Because I
Yeah.
imagine they're not particularly cooperative.
No, they're not cooperative.
Scanning a very precise line alongside
So
the
there
glacier.
is, yeah, so there is paper. There might be more than one, but there's definitely one paper where they derive some of the only measurements actually directly made of subglacial discharge plumes, because the seals forage in the plumes, because the plumes upwell, nutrient-rich water, and so then you get like fish and phytoplankton and stuff, and the seals are eating in there. Yeah, so basically what they did was they captured seals on the ice, so jumped on them effectively and held them down, and then basically they held them down, and then they glued effectively conductivity, temperature, pressure sensor to their heads, and then they let them go. And I believe, and there also was some kind of positioning sensor as well, because they needed to know where the measurement was.
Okay.
And they let them go, and then the seals went off, and they probably were like, people who get abducted by aliens talk about stuff,
Yeah.
right? Like the seals probably like, I don't know what's going on. But it was all above board, right? It was NSF funded research, and so there was, basically seals molt, and so basically eventually the sensor is going to fall off. So the seals went out and they were foraging, and the goal was to basically try to recapture those seals before they molted and get the data. And so they lost a bunch of data because they didn't recapture all the seals, but they got some data back. Positives, direct measurements of a place that's really hard to make direct measurements. Negative, not all the seals went to the subglacial discharge plume. Some of the seals probably were like, I'm not coming back to the surface for a long time because these crazy people stopped things in my head. So they lost a lot of sensors, but the sensors were low cost, right? And so negative being that you can't tell seals where to go. Or we can tell them, but so right. So I mean, I think really creative, also really crazy. Yeah.
Sounds like some like Cold War scheme.
It sounds like, trying to tell dolphins, train dolphins to do stuff, which, yeah, Mike?
Building off that, so, no, it's not totally related, but if the seals are going to the plume for biological activity, and you had shown in your figure that the plume was standing out relative to some unknown area with possible biologics, how are you sure you're not just in training on biologic responses versus
It could be.
oceanography?
It could be, yeah. I mean, so the scattering mechanism is not been determined. And in theory, the elevated scattering that's associated with sort of the plume geometry could be due to biology. It's possible. I think you'd have to have a lot of biology to get at the sort of scattering intensities that we're seeing there, at least in the really intense regions. And we don't see any evidence sort of around the plume of like a volume scattering signal that looks anything like, groups of krill or, those types of things, gas-bearing zooplankton or something like that. We do see fish, not in this particular data set, except for maybe like to the west where there were those weird scatterers that I was like, I don't know what these are. We see lots of fish though, in general. But here, if you zoom in, fish are very particular shapes, right? They create these like sort of chevron looking things. No fish in the plume that we could see, but it's definitely possible that there is biology there that we're not seeing, or the scattering is driven partially by biology. That's the kind of question, right? That's the ambiguity that we need to try to break with the broadband scattering. Yeah,
This
Tracy.
is another stupid seal question, but how do the seals stay safe from calving?
Oh, I don't think that they do. I don't really know.
Like maybe it's enough
So
of a
I think they forage there because it's kind of like high risk, high reward foraging, because there's a lot, because the plumes, part of the reason we might care about studying them is that they support a lot of biology because of all the upwelling. So I think the seals are taking a calculated risk. They also might be able to identify that a calving event's gonna happen via some metric. Either we don't know, calving often creates, there's like cracking that happens before calving events. You almost always can hear it and you go, there's gonna be a calving, and then you turn all of your cameras towards the ice face in the hope that you'll capture it, right? So it's possible that the seals are, keyed into that and they're just, or maybe they, especially with submarine calving, right, it kind of pops up and comes up like this, so maybe they just go up with, I don't know.
Shot in the air. That's so
I like how you answer. That's confidence.
That's my guess, that would be my guess, yeah,
Please, when you're approaching an iceberg,
sure.
it's the safe distance, it's the length of the iceberg or twice the height. So whichever is greater, so we need you to be safe. But in that case, what is like the closest point that you guys?
To the terminus?
Yes.
Yeah, so, so there is a safety distance associated with the terminus, right? It really depends, part of it depends on the terminus itself. So there are really active, really tall, like exposed termini that are very dangerous. So like LeConte Glacier in Alaska is an example of this. It's much taller than Hansbreen, and it is very active in its aerial calving, so you don't want to get within 500 meters of LeConte. Hans is not as active, there aren't as many calving events, and it's significantly shorter. The closest we got was way too close, was not on purpose. We were taking a CTD station and we were at the edge of a subglacial discharge plume, and it actually pulled us in. So we were sort of sitting on its edge, dropping a CTD, and then suddenly the whole ship was being pulled towards the glacier face. And the engines were out of gear. And so by the time the captain got down to turn them on, we were pretty close. Like, not touching it, but close enough that I went, we're gonna change the procedure for these because that can't happen again, kind of situation. So there is a safety distance. We occasionally got slightly closer than that.
While you're collecting the data, were guys safe enough?
Safe enough.
Okay.
I'm here. I think if I did it again, I think I would implement a stronger safety distance.
Okay.
A more intense safety distance.
Maybe go with the Canadians. Those guys are amazing.
Because they're not afraid.
So, just like quick story, so we were mapping the underside of a glacial, not a glacial, a tabular iceberg.
Yeah.
And on a wall that we weren't as close as like from here to that wall, but it felt like it because the wall was
Very
half
tall.
again as high.
Yeah.
And a chunk of ice about the size of a VW bus calved off right in front of us. And the coxswain of the boat, which was a Canadian Coast Guard guy, probably in his 40s, threw the boat in reverse and backed away from the glacier as just as fast as he could. And this wall of water
Yep.
came at us. And just at the last minute, he throttled forward and the bow popped up and we rode right over the
Yeah.
top. And then we went on the boat we were doing like it was nothing.
Yeah.
It was amazing.
Yeah, yeah. So we didn't have any experiences like that. The biggest thing with calving, other than being crushed, right, would be really actually the tsunami wave that is, that's what we call it, probably from like a physical oceanography perspective. I shouldn't say that because tsunamis have a very particular definition, but the really large wave that is created, it dies off very quickly, but it's very easy to capsize boats, especially if you happen to be, sort of broadside. Yeah, then you're. So that was the part that was scariest when we got pulled in, was because we got pulled in and we got turned, and so we were looking up at the glacier, and we were parallel to it.
That's not fun.
Yeah, no, it was really scary. So I think in terms of looking to the future, in terms of collecting the data, I think we, including myself, need to do a better job of defining safety standards. And part of that was just that I didn't have any experience in a system like this, and I didn't really know how unsafe I had been until I talked to people who had been there before, and then they were like, you probably shouldn't do that again. So,
Were you allowed on deck?
but yes, I was on deck,
Is that because of the wave that's actually,
yeah. A better place to be?
no, a worse
A
place to be?
Yeah, yeah, so we were on deck, there was gear over the side, and CHD was over the side. My collaborators were the ones that were actively using the boat at the time, and I was processing data, and I remember looking up, and I was in the cabin, and I looked up and I saw the ice face, and I couldn't see the top, and I went, it's bad. So then I ran outside, and we were very close, and I immediately was like, we're stopping all the operation, I don't care what's going on with your gear, we're gonna be moving right now, so.
You immediately took a TikTok video.
Yeah, no. I didn't want any video evidence.
Do we have any more questions? No, I think that's all. Thank you so much.